Okay, let's get started for the final session. So the first talk is by Yasunori Hori. Going to talk about refloating planets and stars in the cosmic environment.
Okay, thank you. Thanks, organizer, for the giving time for my talk. So today, I'm going to talk about the free floating planet in the cluster environment. So at this conference, many speakers have already discussed the dynamical origin of the free floating planets, such as the gravitational scattering and also dynamical stability of the system. So in this talk, I'm going to discuss how stellar encounters, sometimes stellar flybys, can help to form the free-floating planet in the cluster environment. Of course, this kind of a topic has been discussed in many papers, including our papers. So, but you know, recently, the planet surveys so suggest provided the new distribution of the information, new distribution of new information of the distribution planet beyond 1 AU. So taking account of this kind of update, I want to try to re-evaluate this formation, the free floating planet around the star in the cluster environment. Right. So in this image, so we see the dozens of bright stars. So this is one of the famous open clusters, the Pleiades. Yeah. So most of the stars are thought to be born in the cluster environment. Even our sun is likely to be being a member of the star clusters. So because the mineralogical records of the meteorite show the injection short-lived radioactive nuclei like aluminum and irons from near massive stars. So that's why most of the stars used to be a member of the star clusters. So there are two types of star clusters, the open cluster and the globular. So planets have been discovered in the several open clusters, like in the Hyades and the Beehive. So this figure shows like the mass range of the nearby open clusters. Each color represented the mass range of the open clusters from 100 to 1,000 times solar masses. So we would say open clusters are groups of tens to the hundreds of stars. On the other hand, the globular clusters were massive star clusters called globular clusters. There are typically 10 to 4 and 10 to 6 stars in globular clusters. So all the star clusters shown here were included the target of the previous planet surveys. So planet surveys around the star in the star clusters began with the radial velocity measurement from the Grant-based telescope. And then transit observation were mainly made by the extended mission, the Kepler Space Telescope, so the K2 campaigns. The number of the known planets in the open cluster is at most the 40s, among 5,800 exoplanets. So some of them in the open clusters produce the multiple planet systems. How about the globular clusters? The star in the globular cluster, they're very old and metal. So twice there are no planets found in the globular clusters. Let me explain the planet survey in the globular clusters. So, the globular cluster, they're too distant from the Earth and they're too dense to observe the individual stars. So that's why the Hubble Space Telescope was used to search for the planet in the globular clusters. So let me explain the reason why the globular cluster is a kind of the desert to the planets. One is, for example, here, for example, the meteoricity distribution, the nearby open clusters. It's a kind of the Gaussian distribution with the mean of the solar meteoricity. In contrast, the metricity distribution of the globular cluster in the Milky Way is like that. We see this distribution is skewed toward the low metricity environment. The globular cluster have metricity typically less than -1. So this means the building blocks of planets around the star in the globular cluster is not sufficient compared to the open clusters. Oh, I should say that, okay, there are no planets found around the star in the open clusters except for the cluster planets. Sorry. Okay, so from here on, I'd like to focus on only the open clusters because we have no planets, no known planet in the globular clusters. So let's consider what happens in the open clusters. The first, front formation around the star in the open clusters may not be efficient. So because cross encounters between the stars occur frequently in the open clusters, sometimes stellar encounter can strip out of the outer part of the protoplanetary disk. In addition, external UV radiation from the massive stars can cause the photoevaporation of the disk. The both effect can reduce the efficiency of the planet formation in the disk. That's what happened. The properties around the star and near the trapezium cluster in heart of the Orion nebulous. This beautiful geometric image to reveal the complicated dynamics of this gas around the star near the trapezium cluster. Right. So what do the planet surveys tell us about the efficiency of the planet formation in the open clusters? So the frequency of the planet around the star in open clusters is not lower than we predicted. In fact, the known planets in the open cluster are very scarce. But this reality seems to be a kind of the observation biases due to the low detection probability of the stars in the open cluster, because usually open cluster is difficult to see from the ground space telescope. Well, what if France is system that common in the open clusters? Is there a uniqueness to the planet formation on the star in the open clusters? One important point is that stellar encounters are not evitable. So the cross encounter between the passing star and the star-planet system can destroy this planetary system sometimes. So meanwhile, one of the planets will be ejected from the system, and then it will become the free-floating planet in space. Also, so this is one of the formation pathway of the producing the free-floating planets. I mean, I don't rule out any other way to produce a free-floating planet, like the gravitational scatterings between the planets and also ejections of planets associated with the stellar evolution, like the supernovas. So, okay. Next, we would like to see the planetary system during the dynamical evolution of the open clusters. The first, I consider two types of open clusters. One is a high density open cluster, like the beehive. The other one is a low density open clusters, such as the Pleiades and the Hyades. So here are the details of our open cluster model. I think that this kind of a setting is a very typical case. The King's model, the powerful IMF, and we include this effect of the stellar evolution, the stellar collisions. Sorry, I'd like to skip the details. So the image on the right shows the central density of the open cluster as a function of time. The left solid line shows a high density open cluster model, and cyan dashed line is a low density open cluster model. So we see that these two types of open cluster model can explain the properties of the nearby, most of the nearby is open clusters. So I would like to focus on these two types of open cluster model in order to see the planetary system in the open clusters. Okay, so this panel shows like the initial distribution of star in the open clusters. The right one shows the spatial distribution of stars after the 600 million years. So each color shows the spectral type of the star. Red one is the B-type stars, green one is the G-type stars. So we see many massive stars tend to stay near the central region, this clusters. On the other hand, these massive stars are located in the, particularly in the cluster halo, like here, like here. So this is because individual stars try to equalize their kinetic energies. So that's why more massive stars will lose more kinetic energy due to the dynamical friction and sink into the central region of clusters. So this is called like the mass segregation. So this means the more massive stars will experience the more cross encounters more frequently. Okay. Oh, so I briefly mentioned one effect. So the effect of the galactic potential on the open clusters. So the stars in the outskirt of the cluster halo pulled out of the clusters by the galactic tide. This means the tidal effect increases the mass loss near the tidal radius. But the most of the mass of the clusters are still loaded within the tidal radius. So that's why the galactic tide does not affect the final result of simulations. All right. So during the dynamic evolution of the open clusters, how can we know whether the planet can be ejected from the system? First, we estimated the energy velocity change by due to the cross encounter. This means the stars the velocity perturbation in the star branch system is caused by the passing star in the short period of time. This is called like the impulse approximations. So using the velocity change, we evaluated the energy change in the planetary system. So if the energy change in the planetary system exceeded the total energy of the planetary system, so we consider that these planets can be destroyed by this cross encounters. So how often do the stellar encounters occur in the open cluster? The rate of the stellar encounters with the distance d from planetary system in the clusters is given by this equation. It is obvious this term is shows like the effect of gravitational focusing. We can understand using this equation. So using these equations, for example, we expect the stellar encounter with 10 AU from the star to occur in the time scale of the 100 million year or more. Okay, let's move on to the result. Okay, first we assumed all the stars initially had one planet at a given semi-axis. But on the next slide, I will show you the result of ejection rate of planets using the observed planetary distribution in the field. So these two figures show the cumulative fraction of the planet ejected from the system as a function of time. The purple one is the ejection rate of the planets between 1 AU and 10 AU. So we clearly see the ejection rate of the planet increase with the time until around here. Beyond this point, the ejection rate of the planet is saturated. In other words, the stellar encounter hardly occurs beyond this point. This is understood as a two-body relaxation process. The star in the open clusters approach to the dynamical equilibrium state through the gravitational interaction, which is the two-body ejection. So this two-body ejection timescale is typically approximately defined by these equations. Sorry, I stupid because I'm running out of time. Okay, so this timescale is kind of comparable to the timescale, the core collapse of solid. Wow. So, but if we consider less massive open clusters, so the two-body ejection timescale is much longer than compared to this. So that's why the ejection rate of the planets increase in time, even though beyond the 100 million years. So, okay, so this figure shows the short period planet like the hot Jupiter is rarely ejected from the system. The ejection rate of the planet between 1 AU and 10 AU is less than 10%. But planets below 10 AU, so wide orbit planet can be easily ejected. So maybe time is now. Okay, so give me a few minutes. So, okay, so next one is the realistic case. I use the realistic distribution planet from the observation of the planet surface. So recently, is the frequency of the gas giant, say, has a turnover around the 2 to 3 AU, around here, like this. This is comparable to the location of the snow line and the sunlight source. So taking account of these new distribution of the gas giant and plus the distribution of planet of the gas giant, distribution of gas giant beyond 10 AU from the direct imaging surface. So I simulate this like the ejection rate of planet in the open clusters. Cool. This is the final result of my talk. Okay. In a low density open cluster case, ejection rate of the planet in total is less than 0.1%. Even for the high density open cluster model, so the ejection rate of the planet, especially gas giant, is at most 1% or a few percent. So ejection of free floating planets by the stellar encounters is very rare, unless the frequency gas giant, the open cluster is higher than its estimated free occurrence rate gas giant in the field. So let me say, this means the stellar encounter in open cluster makes only the small contribution to the formation of the free floating planets. Maybe time. Okay. Okay, I stopped my talk here.
Thank you for the talk. So it was a little quick there, but one thing that I was wondering about is you're talking about the mass segregation of the stars in the cluster. Presumably, if you do liberate a bunch of planets, right, those will also, over some time scale, mass segregate.
Mm-hmm.
You would have heavier free-floating planets fall more towards the center, and lighter free-floating planets sort of evaporate upwards. But I couldn't tell, as you flashed through the slides, from the relaxation time scale, how the scaling went. So is it just, does that take forever?
This one?
Yeah. So it goes with the inverse square root, I guess.
Yeah. Number density of a star is the mean mass of the stars. So, okay, in our simulations, so we simulated the trajectory of the star. So I mean that each star actually, so we consider each star has a planet, but we didn't simulate the orbital motion of the planet on a star because, time scale to integrate the orbital motion planet is much shorter than the time scale of the dynamical evolution of the cluster. That's why it's time-consuming computational problem.
So what was the relaxation time scale for the stars?
Yeah, like only the star.
What was that though? What is the relaxation time scale?
This one?
Yeah, how long did it take?
Oh, typically 10 million years. Typically 10 million years.
So just scaling that equation then down to planetary masses, it would be.
Yeah. Typically 10 million years. Yeah.
Relaxation time depends on the mean mass of the cluster.
Yeah, right.
So unless you're dominated by low mass planets,
right,
it's going to be basically the typical mass of the star.
Yes.
Oh, so the populations.
Yeah.
populations don't separate from one another effectively. It's not that people are kind of talking to each other since they have comparable masses.
So they can't actually achieve equal partition in this case because the planet mass is so much lower than the solar mass.
Yeah.
So they just get ejected from the system.
Oh, so they're just evaporated out. Okay.
Thank you.
I had a question. If there's in the galactic center, it may have been that this initial stellar density when the planets were forming was actually quite high. It formed in kind of a starburst kind of situation. So have you considered whether or not there could be significant tidal stripping in the planets that formed in the galactic bulge?
Oh yeah, actually, so answered yes. So in our simulation, we consider the location of the open clusters as like at 8 kiloparsec. It is a comparable to location of our solar system. So that's why, so in our case, so the galactic tide, it's does not have the strong effect like the configuration of the cluster. But you're right, so in the near the galactic centers, yeah, we cannot neglect it.